In this presentation, we'll return to the topic of stability, but now we'll look at it in the light of our results on transfer functions. So first, let's recall what we learned about stability before. We talked about two different kinds, internal and external stability. Internal stability is when we discussed asymptotic stability, and we looked at the characteristic values. External stability was when we discussed Bibo stability, and the analysis of Bibo stability, if you recall, was taking the integral from minus infinity to infinity of the absolute value of h of tau, d tau, and looking at whether that was a finite number or not. So now let's see what stability means in the context of the transfer function. Let's start with our linear time invariant continuous time system governed by a differential equation. Q of d times y of t is p of d times x of t. We found that the characteristic polynomial of this was q of lambda, and it was the roots of this characteristic polynomial, q of lambda equals 0, that determined the internal asymptotic stability. We found that internal asymptotic stability was equivalent to all roots, all characteristic values, in the left half plane. We saw in our last presentation that the transfer function of this system, governed by this differential equation, was h of s is equal to p of s over q of s. We simply replaced the differential operator d in q of d and p of d by s, and then took the ratio. So examining this, it seems that the denominator of the transfer function is the characteristic polynomial q of s. And so, if we look at the denominator of our transfer function, we should be able to ascertain stability. So the question I want you to consider is this always true? If we look at the denominator of a transfer function, can we determine stability? Is it always the same as the characteristic polynomial? Now, since I'm spending time discussing this, you've probably guessed that the answer is no. And that's correct. This is sometimes true, but it's not always true. Terms in p of s could cancel terms in q of s. In this case, the denominator of the transfer function will not be the same as the characteristic polynomial. In just a moment, we'll look at an example where this happens, where the denominator is not the same as the characteristic polynomial. But first, let's talk about the implications this has for stability. Because the denominator of a transfer function is not the same as the characteristic polynomial, we know that Bibo stability will not imply asymptotic stability. We discussed this before. It's the case of unobservable or uncontrollable modes. While unobservable and uncontrollable modes are depicted in the internal description of the system, the differential equation, they will not show up in the transfer function. Let's now look at an example where there is a hidden mode and where you can see that the characteristic polynomial is not the same as the denominator of the transfer function. The differential equation in this example is y double dot minus y equals x dot minus x, or in terms of the differential operator, d squared minus 1 times y of t is d minus 1 times x of t. So q of d is d squared minus 1, and p of d is d minus 1. So q of s will be s squared minus 1, and p of s is s minus 1. Let's now find the characteristic roots so that we can determine whether the system has internal stability. Q of lambda will be lambda squared minus 1. We can find the roots of that characteristic polynomial as lambda 1 equals 1 and lambda 2 equals minus 1. We plot those in the complex plane, and we see, of course, that one mode is in the right half plane. That characteristic value at 1 indicates an unstable mode. So we have internal instability for this differential equation. So now we've analyzed stability from the internal system description, the differential equation. Let's now do it from the external system description, that is, the transfer function. So I'll take the Laplace transform of my differential equation. I'll assume 0 initial conditions. That will give me s squared times y of s minus y of s equals s times x of s minus x of s. I then do algebra to find the transfer function. I find y of s is equal to s minus 1 over s squared minus 1 times x of s. But we're not done yet. We haven't finished simplifying. So we found that the relationship between y of s and x of s was s minus 1 over s squared minus 1. We'll factor the s squared minus 1 in the denominator as s plus 1 times s minus 1. And then we note that the s minus 1 in the denominator and the s minus 1 in the numerator are like terms and can cancel out. And that leaves us with 1 over s plus 1. So we find that the transfer function in this case is 1 over s plus 1. The denominator of the transfer function is not the same as the characteristic polynomial. What's happening here is there's an unstable pole at s equals 1, and it is hidden in the transfer function, the external description. If we apply an impulse at the input to this system, we'll get the impulse response h of t equals e to the minus t u of t. And we can test this impulse response, and we'll find out that it is Bibo stable, because the integral from minus infinity to infinity of the absolute value of h of t dt will be a finite number. So we have Bibo stability, but we do not have asymptotic stability. The hidden mode is the problem. This is the issue we discussed at the start of our presentation. We asked whether the denominator of the transfer function was always the same as the characteristic polynomial. And our answer was, it could be, but was not necessarily the same. That answer indicates that sometimes it is true. So sometimes we may be able to derive from Bibo stability asymptotic stability. So let's talk about that case. The condition for Bibo stability that you'll find in the text by Lottie says the following. We have Bibo stability if all roots of the denominator of the transfer function are in the left half plane and the order of the numerator is less than or equal to the order of the denominator. That is, m is less than or equal to n. Now, since in this class we'll always be dealing with systems which are proper, that is, where m is less than or equal to n, I'm not going to worry so much about the second condition. So let's concentrate on the first as the real definition of Bibo stability, that all roots of the denominator of the transfer function are in the left half plane. You'll see that if p of s and q of s have no common factors, then there can be no hidden modes. Then the roots of the denominator of h of s will be the same as the roots of q of s, and therefore in this case internal stability will be equivalent to Bibo stability. So if you have a problem where you're told that there are no hidden modes, and you have the transfer function, you know that the denominator of the transfer function is the same as q of lambda, the characteristic polynomial. And therefore, if you analyze the poles of the transfer function and find them in the left half plane, you have Bibo stability. Then you know that you also, from the Bibo stability, have asymptotic stability.